see this problem asks to find the derivative of r at x equals 3. And it's using units to explain the meaning of that value in the context of this problem. So for C, we're going to find r prime of t. So r of t is 600 t over t plus 3. So differentiating this, we're going to get r prime of t is going to be 600 times t plus 3, so I'm using the quotient rule, minus 600 t all divided by t plus 3, and we're going to square that. And simplifying that out, the 600 t's cancel out, so we end up with 1,800 in the numerator and t plus 3 squared in the denominator. Now evaluating r prime at 3, we're just going to substitute 3 into this expression, so we get 1,800 divided by 3 plus 3 squared, so that's going to be divided by 36. So 1,800 divided by 36 is equal to 50. Now this is the derivative of the rate. The rate r of t is measured in liters per hour. So this is going to be the derivative of the derivative, or the rate of the rate. So this will be measured in liters per hour, or hour squared. And this is the rate of change of the rate. Okay, so this is how fast the rate of water flow is changing. For Part D says here, write but do not solve an equation involving an integral to find the time A when the amount of water is 9,000 liters. Okay, so we're going to say that the liters as a function of time is going to be equal to, well, we're starting with 12,000. So we need some starting point, starting amount, and then now we can use the integral to determine the change. Now, since the rate is negative, we're going to subtract that integral, so that at 12,000, at time equals 0, we have 12,000 liters. So we need to make sure that these match. The time is 0, 12,000 liters, and we're going to integrate this to some point A. And we want then the integral under the r of t function. So this represents the integral under the area under the r of t function. This amount represents the change in liters. This represents the change in liters in this problem. Okay, so the total amount of liters is then going to be equal to 12,000 minus the change in liters, and the end point is A, and that should give us a liter value of 9,000 liters. So this represents my equation that will solve for some point A. Okay, so write but do not solve the equation involving an integral to find time A when the value is 9,000 liters, and that is what my integral will look like. Okay, and when I set this up, I can, the difference in the antiderivative, or the area under the curve, as I plug it in, I can solve for the value of A.